In this video, we want to take a look at second-order homogeneous differential equations with constant coefficients that happen to have complex roots to the characteristic equation. Hold on to your bootstraps. So we're looking at this kind of an equation, and we've been saying we think that the answer is going to look like e to the RT. When you plug that e to the RT in, you find that you need to solve this quadratic equation, and that quadratic equation, of course, has two roots which look like this. We are currently looking at the case where b squared minus 4ac is negative. So that square root is yielding an imaginary number. Okay. Now, if I rewrite this way, breaking it into this part and that part, this part in the beginning here is the real part, and the imaginary part comes out of that square root. So the coefficient in front of I is this thing. Notice this was b squared minus 4ac, where this is 4ac minus b squared because I took the minus sign out of the square root to become a minus 1. Sorry, square root of minus 1, which would be I. So what I have is a real part plus or minus an imaginary part, which, for the sake of shortening what I need to write, we're going to write this as alpha plus or minus beta. Right? It's important to note here, or at least interesting to note, that this is always giving us complex conjugate solutions, right? That it isn't just two random complex numbers, but it's always the same real number and plus or minus the same imaginary part. Okay, that these are not just random numbers here. These are complex conjugates is what they're called. Okay. Now, for the rest of this thing, this video, alpha is equal to negative b over 2a, and beta is equal to the square root divided by 2a. Okay, we will plug it back in towards the end, but for the meantime, we got this. So, now, the development of these solutions to differential equations was happening at about the same time that people were really trying to wrap their brains around complex numbers and whether we really should be using them or not. You know, the imaginary numbers get their name from Descartes, who was trying to dismiss them. He was kind of putting them down, saying, just, we've had enough of these imaginary numbers. You know, saying they're not real. We shouldn't be working with them. And yet people kept saying, oh, but look at the things we can do with them, right? I'm here to say there's nothing imaginary about imaginary numbers. They're just not used for balancing your checkbook, things like that. But they are used for other things, for instance, here. So back in those days, you might have gotten to this point and said, well, I assumed that the solution looked like this, and I ended up with complex values for r, so the solution must not look like that. And that's a reasonable thing to say. And then you say, okay, now I need to go looking for another solution, right? My guess was wrong. However, let's just use it anyway and see what happens. So let's just do e to the... This is the R1. So, right, two solutions. I'm using the plus sign for one of the solutions, and I'm using the minus sign for the other solution. So I've got my two y1 and y2. I'm going to rewrite each of these. So the e to the... So I'm distributing the x in here, and then recognizing that e to a sum of the exponents is the product of those two things with the same base e. And I know how to handle this. This is what we worked on in the last video. So e to the beta xi is cosine beta x plus I sine beta x. Okay. Likewise, with the alpha minus beta I for y2, the only difference is that you end up with a sine of minus beta. Sorry, I should have probably had the cosine of minus beta in here as well, but cosine of minus beta and the cosine of beta are the same because cosine is an odd function. But on the sine, sorry, cosine is an even function. That's the point. Cosine is even, so the minus sign in here doesn't make any difference. But sine is an odd function, so the minus on the inside actually becomes a minus on the outside. What are we at? Okay, so my general solution would look like C1 times Y1 plus C2 times Y2. And now I'm just going to do some algebra and move some things around. So for instance, I notice both of these have a factor of e to the alpha x, and so I factor that out. And I think at the same time, nope, I haven't done that yet. So it's still C1 times this and C2 times that. That's where I am here. So now I'm going to distribute the C1 and the C2 in. which is what I end up with there. And now I'm going to recombine. So I get two things I notice have cosine beta x in it. And so there they are there. And I notice two things with sine beta x in it, here and there. And so I've collected them here. Okay. But now, this is where I get to say, hey, Rocky, watch me pull a rabbit out of my hat. C1 plus C2 is just some other constant, right? So I've got some constant times cosine. And C1i minus C2i is also just some other constant. So I'm just going to call that C2. And so what I have here is a completely real function now, provided that C1 and C2 are real. And you might argue, hey, how could this be real? It's like, well, you're thinking of C1 and C2 originally as real numbers, but if they were complex numbers, it's quite possible that both this and that are real. And anyway, I'll admit that's somewhat unsatisfactory. But the result that I get here is that I claim now that e to the alpha x times cosine beta x and e to the alpha x times sine beta x are actual solutions to the differential equation. Okay. These are completely real functions. There's no imaginaries anymore. The imaginaries just went away in the step from here to there. They're just gone. Now, there's a theorem in the section previous to this one that I skipped. This is really the only place we use it. And the theorem says if you have a solution to a differential equation that is of the form some function of x, some real function of x plus some other real function of x times I, then both the real function and, so those two, so f of x plus g of x times I. So f of x is a real function, g of x is a real function, but together they're a complex function. But if that together as a complex function is a solution to your differential equation, then each of the two pieces, the real piece and the imaginary piece, are solutions as well. Okay, this is a much more general result than what I'm doing here. But my claim is this process that I just did gave me two functions that are solutions to those differential equations. And I'm going to check that now. So here's my check. I'm going to just do the y1, and the calculation for y2 will be similar. This is where you're really going to hold on to your bootstraps. So here we go. I need to figure out what y1 prime is and y1 double prime. So here we go. I'm going to slide this up to the top, and we can see what's going on. Maybe I'll get my face up here out of the way. Yeah. So y1 prime. So here's y1, and so there's a product rule. So the first derivative is there's the e to the alpha times the derivative of the cosine of, cosine of beta. So there's a minus beta sine. Yeah, and then the derivative of the exponential part times the cosine. Just because I know what I'm going to do with it next, I'm going to factor out the e to the alpha x, leaving the sines and cosines added together inside here. Second derivative is the derivative of this thing. Again, I'm doing a product rule, leaving the exponential alone, taking the derivative of the sine and cosine, and then taking the derivative of the exponential, leaving the sines and cosines alone. And then doing a little bit of algebra, factoring out the e to the alpha x, and then collecting my cosines and collecting my sines. So the cosine, for instance, I see a minus beta squared, and over here there's an alpha cosine and an alpha there, so there's an alpha squared cosine. That's that. And then the sines, there's a minus alpha beta, and there's also a minus alpha beta that comes from this one. Okay, so minus 2 alpha betas. So there's the second derivative, there's the first derivative, there's the function. Plug them into the original differential equation, and we get this big long thing. Here's a times the second derivative plus b times the first derivative plus c times the third derivative. I'm moving fast because I want to get done within the 15 minutes allotment that YouTube allows me to post. You can slow this down or pause it and take a look and make sure that my algebra is correct. I'm pretty sure it is. So what I'm going to do here is, what am I going to do? I'm going to factor out all these e to the alphas, and I'm going to distribute the a into here and the b into there. So there's the e to the alpha with the a distributed in on this first one, and the b distributed in on the second one. right? Now I'm going to collect the cosines together, and I'm going to collect the sines together. So the cosines have this coefficient and that coefficient and that coefficient. So there they are times cosine. And the sines, I see two of them. There's this one here and that one there, and there's their coefficients. Now, I've got A's, B's, C's, alphas, and betas. But remember, alpha and beta came from the solution to the original equation up here, or the characteristic equation. Where are we? Yeah, I had this quadratic equation for which alpha plus or minus beta were the two solutions. Alpha minus beta I were the two solutions. So alpha was this and beta was that. Okay, so I'm going to now plug those back in so that everything's in terms of A's, B's, and C's and no more alphas and betas. Okay, so if you haven't had enough algebra yet, this just keeps getting better, right? So all of the alphas are being replaced by negative b over 2a, and all the betas are being replaced by the square root of 4ac minus b squared over 2a. And so it gets plugged in here and here. I'm not bothering to do it for that beta and that beta inside the sine and cosine. Just the stuff that's in the coefficients part. So yeah, there's this, and it runs clear off the page that you can't see it here. Can I show it to you? I think I can. Well, if I slide over, yeah, so we get all of that stuff plugged in for all these betas and alphas here. Okay. Now, let's do a little simplifying. This is just algebra, right? It's just a lot of algebra, but still, just algebra. We can do algebra. So what am I doing? I'm squaring those and distributing this a in here. So the a gets into both of those. Combine those to get this. The c is still as it was. This one right here, the two a's cancel out, and the negative negative becomes a plus b. And then I left everything else alone. I didn't do anything. Stuff you can't see is this stuff here now that you can see, left alone. Now, there's a couple of cool things that happen. One is I notice that this minus that is 0. So it's a 0 times the sine of beta. That's cool. And then these here, I say, well, let's get a common denominator and see what happens. So I get a common denominator. So this a gets distributed across that numerator. Actually, the minus a gets distributed across that numerator. And this one I need to multiply top and bottom by 2a. This one I need to multiply top and bottom by 4a squared. So now I've got a common denominator of 4a squared. And notice, I've got an ab squared. I've got another ab squared. And I've got a minus 2ab squared for a total of 0 ab squareds. I have a minus 4a squared c and a plus 4a squared c for a total of 0 4a squared c's. And all of this adds up to 0. And so I have 0 cos beta plus 0 sine beta times that exponential for a grand total of 0. What just happened? I plugged y1 into the differential equation. There was the first derivative, there was the second equation, right? I plugged it into the left-hand side of that differential equation. I ended up with 0. So y1 is a solution to that differential equation. Likewise, y2 is also a solution to that differential equation. So my two solutions, let me point them out, my two solutions were e to the real part of times x, cosine the imaginary part times x. So I had those two solutions, alpha plus beta I and alpha minus beta I. So the alpha is the real part, the beta was the imaginary part. So e to the alpha x cos beta and e to the alpha x sine beta. Those are my two solutions that I can then use to find all other solutions. Anyway, I'm going to have to do some examples with actual numbers and see that this is not as crazy as it looks. Anyway, but I'll do that in the next video.